welcome back. We're having a look at the second derivative, and what is it about the second derivative that helps us determine the nature of these points? What is it about the second derivative? So if we've got our points, we can see our curve, and we can clearly see that it's got a maximum. And what happens prior? So there's our tangent at the top, is our m equals 0 value. Okay, that's our max value. And then the curve starts to decrease, and we get down to some point here where we get a min value. So that's our min value. So what happens here and what happens here? Well, if we draw the tangent at this point here, the tangent's going up, and that represents the first derivative, doesn't it? That represents the m of that line is equal to f dash of x. It's just the first derivative, okay, or y dash. And we can see that it's got quite a big angle compared to the x-axis, some theta. It's possible to consider that it might approach some vertical angle. Not sure about that, but certainly depends on the function, whether it approaches a vertical angle. But you can see that what's going to happen is for different values, this angle is going to get less and less and less until eventually we're up here, the angle with the x-axis. So theta here could be approaching 90 degrees as we come down the curve this way. Could be approaching 90 degrees, which is pi on 2. Okay, and then as we get to here, theta is going to be joining up with the x-axis, so theta will be 0. As we come to here, we can see that we're going to get very steep angles here. Okay, so at this point here, we will get some angle with respect to theta, which will be the similar kind of angle over there. And so, in this case here, the angle will approach pi on 2 again, so the theta will approach pi on 2. And it was the same as the x-axis there, if it's 0, and it'll be the same as the x-axis here as well. So in these couple of locations. Now, what's the implication of that? So if we think about the tan of the angle, the tan of a vertical angle is opposite over adjacent. So when it's on the pi on 2, opposite over adjacent, it'll be 1 and 0, won't it? So it'll be, for all intents and purposes, we'll get 1 and 0. And when it approaches the x-axis, when it's sitting at parallel, tan of the angle will be 0. So for different points on the curve, we're going to get different tan values, and the tan values are of interest to us. So for the tangent lines, in this case here, as we approach up to a particular max point, the angle theta is decreasing, and then as we go along, that means that the tan is also decreasing. So let's just put that as a symbol, I think. The tan theta is decreasing. And then as we go this way, we can see that the function is concave up. Okay, so this one here is concave up. And the next one will be concave down. What will be happening to the angle there? Concave down. Yeah, my pen's not working very well, is it? Fix that up. depends on what's going on. Concave, this one will be going concave down, and we'll be having theta will be doing what? Getting larger and larger. So in terms of our tangents, we're starting to get larger and larger as we move along here. The angle will be getting larger and larger. And that means the tangent is increasing. Alright, so if our tangent increasing, what that's telling us is that we've got some idea of what's happening for our intervals. So we've got to check our intervals. Intervals play a large part in what happens here. So the interpretations that you'll get when you get questioned about this will be related to your understanding of being able to deliberate these intervals. So on intervals where my pen's having fun this morning. On our intervals where the second derivative is positive, we can say that the function is concave up. With decreasing and then increasing tan theta. Concave up. On intervals the second derivative is negative, we say that the function is concave down. Now, what happens if we get to a point where we have a little turn? So there's our concave down, there's our concave up, and we can clearly see there's a transition point. There's a transition point at this x value where there's a change in concavity from down to up. So we call this point the point of inflection. We've been over that before, but the point of inflection occurs when? Or a point of inflection. When does it occur? So if at some point x, so we can write this way, I guess, if at some point x, and we have to often work that out, we do that by considering this idea here, if at some x, which we'll just call a random x, f at that x so we've got a pairing up of points. F of x is 0. And, this is the important bit, and f double dash at that same x is negative then x is a value where there is a local max. Where there is a local x. Now, if at some x the derivative at that x is 0, this is the important part, and the second derivative at that same x is positive, then x is x is a value where there is a local mean. And that's why we substitute them in. Okay, and the final thing is that at x as a point of inflection, f double dash at that x is equal to 0. And what happens to the first derivative? F of x will do what? It changes. That's what it must mean. It changes sign. I'm just going to fit that in a bit better, I think. Changes sign. And this is this changing of the theta angles and tan. So tan and theta change, they increase and decrease. So we've got another way of finding what happens. This is the nature of the turning points. Okay. Are they a stationary point? Are they a turning point? Are they a point of inflection? And so the two things that we do are that we test. So the first thing we do is we test the x values for sine, test x values from the solution of y dash. I'll put it in that form. Okay. We get the x values out of that we solve that for, and we test them in f double dash. So we take those values and plus concave up minus concave down. So we take the x values from the values that we solved in the first derivative into the second derivative, and the sign tells us concave up or down. The second thing we can do is solve. Again, there's a lot of solving, isn't there? Lots of reasons for solving now. We used to just find the x-intercepts, but now we're finding places of concavity. Solve that x value. Solve fx is equal to 0. Then that x value is where you'll find a point of inflection. A point of inflection. So we've got to follow all those steps through. It's quite a bit of work. So in a formal sense, that's the kind of thing that we want to do. So remember your intervals, because that's the way it'll be expressed when we examine for it. All right, that'll do for now. We'll come back and maybe we'll do an example. We'll see you soon.